Okay, hello everyone. How are you doing today?
Good. Good.
Okay, so I think Professor Cameron wants to make some announcements and then we can get into the class material.
Yes, many of you received emails from me both here and at Caldwell. Just confirming the times that you said you were available to mentor. Many of you have responded to me. I was just double checking to make sure I had your availability correct. What I'm going to do next, over the next 24 hours, is connect you to a team for you to mentor. We have 65 community college students in 11 teams signed up so far, and all 11 teams would love to have mentors. And so soon you will be mentoring. In cases where it's possible, I will assign 2 mentors to a team because I realize that you haven't mentored before and you're right at the beginning of this, and it can be less anxiety provoking to have another mentor to mentor with you. So where that's possible, I'll assign 2 mentors, but it won't be possible all the time. I am always very available, and I will send you detailed instructions. I'll connect you to the faculty member at the community college, and I will connect you to the teams. We also started a community college Slack site for the fall 2025 DataJam season, and I will connect you to the Slack site, and I will connect you to your team on Slack. You will also be getting by email, and I will post it in the for Pitt students in Pitt Canvas. I will send it to Dr. Ferrara, who will probably post it at Caldwell. A 1-page agreement of your agreed on interactions with students online. The DataJam has a policy such that you are fully clothed when you are mentoring, you do not swear, and so on and so forth. And it's very important that we get signed agreements from every mentor back before you start mentoring. So it's very exciting. It's fun to see mentoring starting. And any questions you have, you're welcome to email me.
Okay, sounds
Yep.
good.
That's good.
Any questions? Anything that you want to clarify? Okay. Now what I want to do today is we're gonna get into some more advanced, let's say, data science methods and techniques. And now Excel will not really be an ideal software that we can use to do all these analysis. What I want to do is I want you to start working on the handout. So basically, I'm going to give you around 30 minutes, and I really want you to go on this week handout, and I want you to do the first activity. So basically, the first activity is about installing R&R Studio. So R&R Studio will be the software that we'll be using in this specific lecture to get into the more advanced topics. So please spend around 20 to 25 minutes, let's say 30 minutes, and then go through the first exercise. Make sure that you are able to install R. Make sure that you are able to install R Studio, and then do those simple exercises that I have in this first exercise of the handout. Okay, so please start working on this, and then we can reconvene to get into the actual techniques. Now let's go in week 4, the slide says for week 4. Let's see what we have here. So most of the high school students, they're gonna use, let's say, Excel to do their analysis. However, if you want to do some more advanced analysis, some more advanced methods or techniques, you need another software. And that's why I ask you to install R&R Studio on your computer. Now, I'm sure you have heard about machine learning methods. Now, what is the difference between machine learning and machine learning method versus, let's say, a statistical method? Usually, if we're talking about a statistical method, or let's say general statistics, our main focus would be on the inference. And what do I mean by the inference? Let's say I have two variables. I want to see what's the relationship between the variables. I want to see if this relationship is significant, is not significant. So I'm exploring the relationship between the variables. Now, when we're talking about the machine learning techniques, usually the main focus of these techniques is about prediction. So let's say you have some unseen data, and then you want to make some predictions for those unseen data. Now, this distinction should not be viewed as absolute, but rather as reflecting the primary goals of the two approaches. For example, when you're talking about statistical models, let's say we cover a linear regression, of course, we're still able to do some predictions. It's not like we're not able to do predictions, but it's more about the main focus of these techniques. Now, machine learning methods, some of them, they may also give us a chance to perform some statistical analysis. Here we're looking about the general idea and the, let's say, the primary goal of each one of those groups of techniques. Okay, now, in statistics, let's say when we're talking about statistical methods, we typically work with what we call parametric statistics. And what is parametric statistics? Basically, we define the model in advance. So let's say we have a scenario, we have some variables, and then we decide, I'm going to feed a linear model in our data set with these explanatory variables. These will be my response. And that's basically what we're doing in previous lectures. We had some data sets, we're feeding linear regressions, we're seeing if the slope is significant, and we try to explore what's the relationship between these two variables. Now, what are the advantages of those statistical methods? The first advantage is that the statistical method can often be used with relatively small sample size. And why we're able to use a small sample size to apply those techniques is because we have very strong assumptions in those statistical models. Let's say in our linear model, we assume that the relationship is linear. We assume that there is that relationship between the variables, that specific relationship between the variables. We also assume that the errors are normal. There are a lot of assumptions that are behind those statistical methods. And because of those assumptions, it also makes it easy for us to do an inference. We were able, because of those assumptions, to talk about the hypothesis testing, to define confidence intervals, to estimate parameters because of those assumptions. And it's easy to compute. If you remember, when we get into, let's say, the linear regression, we're able to find a closed form of, let's say, the slope, the intercept, and that's what basically Excel was doing. It has a closed form for the slope, for the intercept, plug in the values, and we get what is the number of what is the value of intercept, what is the number of the slope. Now, what is the disadvantage of those statistical methods is that if the underlying model is wrong, then the results are meaningless. So let's say if we have some data set and the relationship is not linear, and then you decide to apply the linear regression, then the results that you're going to get will be meaningless. You can still apply the linear regression, you can still do your data analysis, you can do all the things that we have learned, but these are meaningless. They don't have any point. You should not really use them to make any predictions or interpret any of the results. Now, on the other hand, machine learning techniques, usually, they don't assume the form of the function ahead of time. So in other words, we're not going to assume at the beginning that there is a linear relationship. There is a quadratic relationship between the variables. What we're going to do is we're going to use the data to find the function that is going to, let's say, summarize the general pattern of the data. Now, in these machine learning techniques, usually we don't have assumptions. We don't have a lot of assumptions about the form of the function. The model can be very flexible because it's basically decided by your data, depending on what are the data, what is the data, then this is going to decide about, let's say, the format of the function. And the resulting functions are often complex and may not have a closed form. So unlike the traditional statistical methods, a lot of machine learning techniques are what we call black box techniques, meaning that we have the data, we have the technique, we give the data to this black box method, and then we get the result. Now, what happened inside that situation there, I may not really have any idea. I may not really have a clear idea what are the steps or how this method works. Now, the advantage of these machine learning techniques is that if you have enough data, then we'll be able to get some very accurate predictions. If you have a lot of data, these machine learning techniques are actually very powerful when we want to make predictions for some unseen data. Now, the disadvantage is that it requires a lot of data to do, let's say, a good job with the machine learning techniques. And we have a limited ability to do inference because we will not really know all the details regarding those techniques. I may not have closed forms for different things. So these make it very hard to basically do inference and also make it very hard to interpret the result. Let's say when you have the linear regression, it's very easy to say, you can see the scale of plot what's the relationship. As you increase one, you see increase in the other one. But when you're talking about these techniques, the machine learning techniques, in a lot of scenarios, it may be very hard to explain and interpret why we get these results. Any questions so far regarding, let's say, the difference between statistical methods versus machine learning? Okay, now, most of the statistical and machine learning techniques, methods, or algorithms are divided into two big groups of methods, depending on, let's say, on their goal. We're going to call the first group of methods to be what we call supervised techniques. These are algorithms that maps an output, an input to an output. So basically, when we have labeled data, is when I have an explanatory variable, and I want to see how this variable affects or influences my response. Basically, all the scenarios that we have seen before had a clear response in mind. I want to predict the number of crime. I wanted to predict the proportion of people that they're gonna vote. I have a clear variable in mind, and I want to be able to, let's say, predict that variable. Now, under the supervised methods, we have a lot of techniques. We have the linear regression. This is the one that we've covered in previous lectures. We have the logistic regression. That's the method that we're going to cover in today's lecture. There are support vector machines, naive Bayes, decision trees. We're also going to talk about decision trees. There is the k-nearest neighborhood, neural networks. All these techniques are what we call supervised techniques. I have a response that I want to predict. Now, on the other hand, we have what we call the unsupervised techniques. So here, I don't have a clear defined response that we're trying to predict. So I have some data. I don't have a response. I don't have something that I want to predict, but it's more about doing an explanatory data analysis. So I have the data and I want to see what's the situation, what's the relationship between the variables, and then I'm going to do this, let's say, exploratory. I'm exploring the data. So I'm doing some exploratory data analysis, and there are different techniques like k-means clustering, again, neural networks, and then PCA, principal component analysis, and a lot of other techniques. Now, why I'm mentioning these techniques? I want you to be aware that such techniques exist just in case you encounter when you talk with the high school students. Most of them, they use correlations, they use linear regressions, but some of them, and as we observe through the years, more and more high school students, they do more advanced stuff. So it's good to know that these methods, these things exist. Now, most of these more advanced techniques, they need languages like Python, R, Java, to implement those things. So Excel will not really be a nice tool for us to use when we want to do those more advanced techniques. So that's why in the first activity of the handout, I ask you to install R in RStudio. And then after the lecture, we're going to get and see how we can use R in RStudio to perform all these techniques. Okay, now, let's see what we have. So the type of analysis, or let's say the model that we want to apply, depends heavily on the type of the response. So what is the response? The response is the variable of interest, is the variable that I want to study. Now, depending on the type, we may need different techniques. So far, in the previous 3 lectures, we talked about quantitative data. And the response basically was quantitative. So if you remember, we had numbers of reported crimes, we had voters turnout rates, we had the values of houses in Seattle area. So we had all these different numeric responses. And our goal was to see what's the relationship, different variables we wanted to predict. Now, there will be some cases where the response will be categorical variable. So for example, I have, let's say, the medical condition, stroke, drug overdose, or epileptic seizure. So let's say a person arrives at the ER, the emergency room, with some conditions, and then you need to be able to identify what is the medical condition of that patient. So then I will not have a numeric variable, but now my response will be more like a categorical. I have different categories. Or let's say you want to, let's say, predict the type of play run in NFL. Pass or rush, or let's say quality, you have a quality score, good, fair, poor. In these scenarios, the response is more like a category. I have different categories, and I want to be able to predict or let's say study these categorical response variables. Now, regarding quantitative responses, that's what actually we talk about in the last 3 lectures. We talk about correlation, we talk about linear regression. All these were related to quantitative response. Now let's get into the categorical response. So anytime the high school students, they have project where their main goal is to study a categorical variable, then we need to be very careful what technique they should apply. Now, the first question is, can we apply the linear regression? And by the way, these techniques are called classification problems. Anytime your response is a categorical variable, then we're going to call that problem classification problem. Now the question is, can we use the linear regression? We have seen the linear regression, we know how to apply it. Can I apply the linear regression anytime my y is a categorical, is not a number anymore? In general, I would say that linear regression is not appropriate when the outcome is categorical variable. And why this is not appropriate, why the linear regression is not appropriate. So let's say if I'm considering the scenario about, let's say, the medical condition. So as I said, a person arrives, let's say, at the emergency room with some symptoms, and then I want to see what is the medical condition of that patient. Then I have these 3 different responses. Now, if you want to apply a linear regression, you need to give some values to those responses. Now, let's assume that you give the value 1 if it's a stroke, value 2 if it's a drug overdose, the number 3 if it's an epileptic seizure. And let's say in this scenario, you get the data set, you get all the necessary information, you have your explanatory variable, and then you fit the linear regression. Now, the first problem is that why you encode these categories as 1, 2, and 3? Why you keep this order in the data set? There's not really a specific reason why you need to keep this order. You may have, I don't know, let's say 3, 1, and 2. There's not really a specific reason why we need to have this enumeration, this coding for the different categories. Or you may even have 10, 20, 30. Why don't you have 1, 2, and 3 for those categories? But as you can imagine, those different values, they're going to give you a different model. They're going to give you different results. So it's very important, anytime you have categories as the response, to be careful to apply the linear regression. Now, there are some exceptions. There will be some scenarios where the linear regression could be applied. And these scenarios are when you have what we call ordinal data. So let's say if there is a natural ordering between the categories, it may make sense to use that 1, 2, and 3 notation. Let's say if you're talking about the good, fair, poor, okay, there is like a logical order between the categories. Now, if you decide to give, let's say 3, 2, 1, okay, then there is kind of a logic behind those one. So then it may make sense to use the linear regression. But in general, we avoid to use the linear regression anytime we have categorical variables. Now, a very interesting scenario, and that's actually very common in practice, and I have seen in a couple of projects, is when you have a binary outcome. And what do we mean by binary outcome? You have 2 categories. Now, the response is either a success or a failure. And usually in statistics, we denote 1 to be the success and 0 to be the failure. Now, the good news is that if you have a binary response, then your white hat in the model, in the linear model, will give you what is the probability that you're gonna get a success. So your y hat will be the probability of getting a success. However, even though in these scenarios, you may be still able to, let's say, apply the linear regression, we need to be, again, a little bit careful. And here I'm showing you this graph. So here I have the linear regression. I'm applying the linear regression. That's your y hat. Now, why the y hat is the probability of the success? You need some calculations. You need to do some calculations. I'm not really going to get into the details. And I don't really want you to know how we get that probability here. But what I want you to know is that in the case where you have a binary data, then the y hat will be the probability of success. And then you model, let's say, that probability with a linear model. Now, let's say you have the data. Now you can see that the data has two categories, success and failure. Some values to be 0, some values to be 1, and then let's say you are feeding a linear regression. Now, what I want you to observe is that in this scenario, if you use the linear regression to make predictions, there will be some values that they're going to give you a negative predicted response. But now my response here will be the probability of getting a success. How can I get a negative probability for success? This does not really make sense. Now, to overcome this problem, anytime you have a binary and you want to apply the linear regression, is instead of applying just a straight line through the data points, is to find another function, another curve that can be within my interval from 0 to 1, because here we're talking about probabilities. I think the color left or yeah, so basically it's between 0 and 1. So I want a function now that it does not really go outside of the range of the data, because think about here, we're talking probabilities. And if you use a linear model, the linear regression, then you may get some negative values for the probabilities. But now if you're able to find a curve, a function that is inside the range of the data, then all the predictions will be between 0 and 1. And it makes sense because we're talking about probabilities here. Now, in general, you can use any function that goes from 0 to 1 to make predictions. Now, a very standard function that we use, let's say in statistics, is basically this specific function. So instead of having, let's say, a linear relationship between your response and your explanatory variable, now you're going to have a function, a linear function of the explanatory variable. So in other words, your response will be equal to the e to the power of the linear relationship between the explanatory variable, and then you divide by 1 plus e to the linear equation using your explanatory variable. Now, in general, theoretically speaking, you could use any function here to model, as long as it goes from 0, 1, because here we're talking about probabilities. Does it make sense? We're saying here. So I have binary data, 0, 1. Now the response will be the probability of success. Now, if you feed a linear regression, you may get some negative values. So that's why you better feed another curve, not just a linear curve. And this curve will be, will make the linear regression what we call as a logistic regression. Anytime you use this specific function, you don't just use the linear equation, but you use a curve, a function of that linear equation, and this is what will be what we going to call the logistic regression. Now here actually I have a resource that's a textbook. It's a very nice textbook that covers more advanced, let's say, data science techniques. So if you want to learn some more of these techniques, so I suggest you find this textbook, and then they also show actually how to run the code, let's say our code, how to get apply linear regression, logistic regression, and a lot of other more advanced. Now let's formally define what is the logistic regression. So logistic regression is a statistical model that is used to predict the probability that outcome from a categorical variable with two categories will occur given some predictor variables. So in other words, I have some explanatory variables. Given those explanatory variables, I want to now predict the value of the response, but the response has two categories. I don't have numeric values anymore. I don't have a lot of categories. I just have 2 categories. Now, your logistic regression equation will look like this. This will be my model. Now, my predicted response will be a function of that linear equation where P of y equals to 1 is the predicted probability that the event will occur given that the predictor value is basically x. Yes. Now, if you play around with that equation, then you're gonna end up with this specific expression here. Let's say the log of the probability of y equals to 1 divided by 1 minus the probability of y equals to 1 will be equal to beta hat, beta 0 hat plus beta 1 hat times x. Now this should remind you of the linear model. Now I have a linear model, but not for the y hat, but for this log expression of the y hat. Now this transformation is what we call the logit, and this is what is usually used, let's say, when we are performing the logistic regression in R and RStudio. You need to know that logit function. There are different functions that you can apply, but the most common one is the logit function. Okay, now to apply, let's say, to get the predicted probability. So basically what we're going to do is we're going to apply the logistic regression in R. You're going to get those coefficients, beta 0 hat, beta 1 hat. And once you get these coefficients exactly the same as when we're applying the linear regression, then you plug in the values and you're going to get your predicted response. Now the predicted response will be the probability of getting a success. Now, if this probability is, let's say, greater than 50%, then we're going to say that this outcome should be a success. If the probability is less than 50%, then we're going to say that this is failure. Any questions? Now, of course, nothing can prevent us from having more explanatory variables. Why I need to have one x to predict the y? I may have more than x. And here I have more than one x's. And so here I have what we call the multiple logistic regression. And for example, here I have, let's say I want to identify whether a voter voted for Biden or Trump in 2020 election. First of all, once you read this scenario, I want you to identify that we are having a categorical response variable. Do you agree with that one? What I want to predict is basically a categorical variable. And not only that, it's also a binary. Why it's a binary?
You're only picking from 2 candidates and you're excluding all sorts of variables.
Yes. So here I'm going to consider just 2 categories, Biden and Trump. So I'm going to denote one to be, let's say, a success, the other one to be a failure. It does not really matter which one you're going to have as 1 and 0, because if you find the probability of 1, you can also find the probability of 1 minus that. So it does not really matter. So here, let's say I can denote Biden with 1, Trump with 0. Now, I may be interested to see how different variables may affect the response. And here I have some examples of the explanatory variables. Maybe you're going to consider the age. How the age affect whether you prefer Biden, you vote for Biden or Trump. Or let's say your residence can really affect your voting preference, or let's say your education level. All these are some variables that they can really affect my response. And then instead of having just a single x, just a single explanatory variable, you can have a logistic regression, but instead of having one x, now I'm going to have more explanatory variable. Does it make sense? Okay. Now what I want to do is, let's go in R. And now you really need to follow my directions to be able to read the data set in R and RStudio. What I want you to do is, I want you to download the data set posters. You can find them in week 4 in the class lecture material. And then I also want you to download the R activity. So let's say if you go in Google Drive, let's say class activities or not class activity, lecture material. I want you to download on your computer both the dataset, posters.csv, and then the R activity.r. So please download them and place them on the same location on your computer. Now, once you download the data and the R code, what I want you to do is I want you to double click on that R activity. So if you double click on that activity, then this activity should open here in R Studio. Are you able to open the R activity? So download data, download the R activity on your computer, and then double click on the R activity. Yes.
Show where you downloaded data from.
So Google Drive is inside the lecture materials.
Your class activities.
So once you download the data set and the R activity, then you double click on the R activity, and then these R script should show up in your R Studio. Were you able to get that?
I think mine's opening up in the R, not in the R.
Okay, so then go open with and then use the R Studio. So we want to open this R script using the R Studio. Now, until you all have these R activity open in the R Studio, let me give you a quick introduction, let's say, to R Studio. So you can see the different tabs in the R Studio. So this tab here is what we call the console. And what is the console? Is basically the area where you can run all your commands, all the code that you have. So let's say maybe you want to run some calculations, 1 + 2, then you just type that command in the console. Or you may actually can even use variables. So you can say x = 3 or 4, y = 2, and then you can do x + y. You can use those variables to define different values, and then you can run all these commands. So this is basically our R console. Now here you can see there are different tabs on this part of the R Studio. The one that I want you to pay attention to is the environment. So here is basically, it shows all the variables that you define. So here, let's say I define X variable, I define Y variable. When we read the data set, all these should show up here in the environment. Then there's also history. This is going to show you all the previous commands that you run in the console. And then at this part of the R Studio, you can find your files, the plots. Let's say if you created some plots, and then some packages that we're going to see in a minute what I mean by the packages. Okay, now what we're going to do is for this activity, we're going to use the coasters.csv file. Now in this file, I have data for 123 roller coasters. And what information I have here? I have, let's say, the name of the coaster, the name of the park where the roller coaster is located, the material of the track, the maximum speed, the highest point of the coaster, the length between the largest gap between, let's say, the high and the lower point, have the length of the roller coaster, the age, the design, and let's say the number of times the roller coaster flips the passenger. So have different information about the roller coasters. Now, how do we read the data set? The first step that you need to do is you need to tell R where to go to find the data set. To do that, what we need to do is you need to go to session, set working directory to source file location. So have their activity, have the data in the same folder, and then what we're going to do is you go session, set working directory to source file location. If you click this command, you're going to tell R where to go and find the data set that we're gonna use in this specific example. Now, if you click on that one, then you're gonna see that it set the working directory. Here it should show the location on your computer where you have the document and the data set. Any questions so far? Okay, so once you set up the working directory, so let me repeat one more time, session, set working directory to source file location. This is gonna tell R where to go and find the data set. Now, what we're gonna do next is let's read the data set. To read the data set, we're gonna use a built-in function in R, and it's called read.table. So there are different functions depending on the type of the data, but if you have a CSV file, one way to read the data is using the read.table function. Now, how function works in RStudio? Functions have names, so it's very important to use the correct name, the precise name. Here it's lowercase read.table, and then you need to use a parenthesis. Inside the parenthesis, you need to specify different arguments. For this specific function, the first argument is basically the name of the data set that you want to use. So in this scenario is the costers.csv, and you need to write the name into the quotation marks. So you make sure that you have the correct name. So if you download the data set multiple times, the name may have changed. Let's say costers parenthesis 1 or 2, or make sure that you have the correct name. And then you use the name, you write the name inside those quotation marks. Then the next argument here is headers equals to true. What is this one? This is telling R that the first row is basically the name of the columns. So let's say if you go here and in the data set and you open the data set using Excel, what I want you to observe is that the first row is basically the name of the column. So here you can see the first row is giving you the names of the different columns, so the costers, park, type. So I want to let R know that don't use the first row in your analysis. It's just the name of the columns. And then the data set are separated by commas in the data set. And then you can run this command to read the data set. Now, what you need to do is not enough to just run this command, this function, but you also need to save the data set in an object. So R is what we call an object-oriented language. You need to have different objects. And here, it's not enough to just read the data set, but you need to save it in an object. And here I'm using a name costers. So if you run this command, now how do you run this command? There are different ways. One way is you copy and paste this command in the console, and then you click enter, and then you can see that now you're able to run the data. In the environment, you can see that here I have a data set. It's called costers, 123 observations, 11 variables. And if you click in this triangle, you can see all the different variables that we have in this specific scenario. Another way to run this command is if you don't want to copy and paste it, you put your cursor and then you go here and then you click run. If you click run, then this will run the command in the console. Any questions on how to read the data set? Usually, actually, that's the step that most of the students struggle with, reading the data set in R and RStudio. Any questions, any comments, or any clarifications? Are you able to run the data set over there? Any questions from Caldwell University? Were you able to read the data set? Because that's the most important step actually in our analysis. Okay, so assume that you don't have any problems, you are able to read the data set. Now let's start doing our analysis. The first analysis that I want to make is, let's study the maximum speed of these clusters, and let's get some more information about the maximum speed. Now, how do I get that specific column from the dataset? So our dataset is called clusters. So if you start typing the dataset in the console, you're gonna see that it shows the dataset. So you have the clusters, but let's say in this specific scenario, I want to know more information about the top speed of the clusters. Now, to get that specific variable, what I'm gonna do is I'm gonna use the $sign. If you click the name of the dataset and then you click the $sign, then it's gonna show you all the different variables in the dataset, all the different columns in the dataset. So let's assume that now I want to use the top speed, top_speed. I want to know some more information about that one. And then let's say you can run this command. Now, if you run this command in the console, then you're gonna see the values for the top speed. Now here you can see the raw data. Now let's say I want to see some summaries for this one. So what I'm gonna do is I'm gonna have the clusters $sign tops_speed, and then let's assume that I'm gonna use the summary function. Let's see what we get if we run this summary function. If you get this summary function, we get some descriptive statistics about the variable. So for example, here you can see what is the minimum value in your data set? What is the mean, the average? What is the maximum? And then you also have some quartiles here. So let's say for the people that are familiar with quartiles, the first quartile is telling you that below that value, I'm going to have 25% of the observations. Media is the 5th percentile or the second quartile. Below that value, I'm going to have 50% of the observations. And similarly for the third quartile, I'm going to have 75% of the observations. So if you use the summary function, this can give you some nice descriptive statistics for the variable of interest. Now you can also use some other variables. Let's say I would find the average. Then you can use the mean function. It's called mean. Then clusters, $sign, let's say the top speed, enter. Then we get this, the mean. Don't worry about the warning messages. Warning messages does not really prevent you from running the code. Only if you get an error, then you need to be worried what's happening, what's going on there, and I'm not able to run the command. I can also calculate the standard deviation. You remember we already talked about the standard deviation. The function in R is called SD. And then again, parentheses, clusters, $sign, and then let's say top speed. And then you run this command, and then you can get what is the standard deviation. Now, I don't want you to memorize any of these functions, but I want you to know that there are some functions that we can use in RStudio to generate all these different things. Now, if there is a function that you don't know, let's say I'm talking about the mean function, and you want to know some more information, then what you're going to do is you click in the console, the question mark, and then you write the function. Let's say question mark v. If you run this command, now in this part of the RStudio, this can give you some more information about this function, about the name, about the different arguments of the function, and then it can also give you some examples how you can run this specific command, let's say in RStudio. Now we can also create plots. And actually R is very good at creating plots. Let's say I want to create a histogram for the top speed. So what I'm going to do is, the good news is that there is a built-in function. And what do I mean by built-in function? Someone else code that function for us, and it's already stored in RStudio. And then I'm just going to call this function and then do the thing that I want to perform. So here the function is the HIST. This function can be used to create a histogram. And then let's say I want to create a histogram for the top speed. $sign, clusters, $sign, and then you choose the variable. Let's say top speed. If you click this one, then now create a histogram for the variable top speed. Any questions? Of course, there are different things that you can do with these graphs. You can change the colors. You can modify the x-axis. You can modify the y-axis. You can do a lot of things in R regarding those graphs. Now, the most interesting questions are usually when I want to explore the relationship between two variables. And in this scenario, let's say I want to see what's the relationship between the maximum height and the top speed. I want to see if there is a relationship between the maximum height of the coaster and, let's say, the top speed, that the maximum speed of that coaster. So in other words, I have two quantitative variables, and then I will see what's the relationship between the variables. Now we know that we can construct a scatter plot to see the relationship between two quantitative variables. Now let's see how can we construct a scatter plot in R. So to do that, I'm going to use the plot function. So the plot function has two arguments for the data. The first argument is basically the values of the explanatory variable. The second argument for the data is my response. So here what I'm going to do is I want to use, let's say, the maximum speed. So coasters, $, maximum height. And then I'm going to use the coasters, $, top speed as the other variable. If you run this command, now I want you to observe, actually, I can zoom in this graph. Now we can see that we have a scatter plot where I'm going to use the maximum speed as an explanatory variable. So in other words, I want to see how the maximum height of the coaster can really affect or influence the maximum speed of that coaster. Okay, now I want to hear from someone. How can you describe the relationship between the maximum height and the top speed? And if you remember, anytime we wanted to describe a relationship, we talk about direction, positive, negative, neither, talk about the form, linear, curve, or let's say no pattern, and then about the strength. You say it's moderate, weak, or a strong relationship. Let's start with the direction. So what is the direction in this specific scalar plot? Yes.
It's positive
Why it's a positive?
because as the x-axis increases, the y-axis increases.
Yes. As we're increasing the maximum height of the coaster, we observe that we also have increase in the maximum speed of that coaster. So you can see that upward trend in the scalar plot. So I agree, there is a positive relationship between the variables. What about the format? Is it linear? Is it curved? You don't see any pattern. What about maybe someone from Caldwell University? So what can you tell about the form of the relationship? Is it linear? Is it curved? Or you don't really see any pattern between the maximum height and the top speed?
Seems to be linear
Okay, so I agree. Why it's a linear?
because it's growing.
So basically the rate of change, so the rate of change of the response is kind of constant. A very nice, simple way to decide is, let's say, if I feed a straight line here, this would be a nice summary for the general trend or pattern of the data. So I agree, it's linear, so have a positive linear. What about the strength of the relationship? Do you think it's strong, moderate, or weak? Sorry. Okay, some people said strong.
Moderate to strong.
Some people said moderate to strong. Okay, now actually to decide about the strength, we know a metric. That's a correlation. The correlation will give us the strength. So let's run a command in our studio to find what is the correlation. And to get this one, I'm going to use the COR function. So be careful about the names. We need to use the correct names. And then I want to find, let's say, the correlation between the maximum height and then the top speed. Oh, you actually have a typo. So make sure that you use the correct names, coasters, $, and then the top speed. Now, if you run this command, now we get a 0.85 as a correlation. And if you remember, I gave you kind of a rule of thumb there. If it's above 0.7, the relationship is quite strong, the linear relationship. So in this scenario, we can tell that there is a linear, positive, strong relationship between the variables. Any questions so far? Any comments? Okay, now once you identify that you have, let's say, a linear relationship, let's fit the linear regression. We know how to do in Excel. Now I'm going to show you one way to fit the linear regression in R. To fit a linear regression, again, we need a command. And this command is what we call the LM. This function is called LM, linear model. And then we need to specify two variables. One is the response, the other one is the explanatory variable. So you can see there is that tilde sign here. Now, before the tilde sign, you need to specify your response. In this scenario, my response, the one that I want to predict, is basically the top speed. And then after the tilde, you need to specify the explanatory variable. And in this scenario, I want to have the maximum height as the explanatory variable. And then you need to also set to R what data you're going to use. And then you have the data equals to clusters. So here, basically, if you run this command in the console, then basically you fit the linear regression. And now you can see what is the intercept, what is that beta 0 hat, and what is also the coefficient for the slope. That's the maximum height. Usually in R and R Studio, because as I said, it's an object-oriented language, if you want to use the results from the linear regression, you need to save the data into an object. That's very important. Anytime you do some analysis in R, you run some commands, you better use an object. You better use a variable, and then you assign the value into that variable. So in this scenario, what I'm doing here is I have model underscore 1. So basically, I'm giving a name to this specific linear regression. And why I'm giving a name? Because I want to use it. I want to use this model to, let's say, create, maybe fit the linear model into my plot, in the scatter plot. I want to fit that line into my model. So what I'm going to do is I'm going to define an object called model underscore 1. If you run this command, then you're going to see that you have your linear model in the environment. It's model underscore 1. If you click on that one, you can get all the different information. You can even run a summary here. So let's say if you have summary of model underscore 1, then you can get all the different information regarding this model. So for example, you can see, okay, the formula that you use, the descriptive statistics that you have, and then you can see what are the coefficients, let's say the intercept, what is the slope. We can also get the standard errors. You remember we talked about standard errors before, and then you can even get the p-values. And here you can see that p-values are very small values. So anytime you see that e, it means it's 10. So here I have 10 to the power of minus 16. It's a very small value. So this is telling you that in this scenario, the slope is statistically significant. Indeed, there is a relationship between the maximum height and the top speed. But in any case, here you can get all the different information regarding the model. Now, how can you fit that line in the scatter plot? You need to use the upline function in R. So if you run this command, this is going to plot your straight line into your scatter plot. Any questions? So if it's your first time coding in R and R Studio, it may be a little bit weird, all these commands, but as you get more practice, then all these will make sense, and they will gonna seem more, let's say, natural, how we define all these techniques. Now, another thing that I want to mention, and that's the last thing that I want to say about the linear regression, is how do we make predictions? Because before, if you remember, we were talking about Excel. In Excel, the main goal of the linear regression is I want to use that model to make prediction. Let's say I want to predict if a roller coaster has a maximum height of 50, what will be the top speed of that roller coaster? Now, to make predictions, what we're going to do is, of course, you can do manually. You have the slope, you have the intercept, plug in the values. Alternatively, you can use that predict function in R. So predict, then you need to specify the model. First, you specify the model, and then you specify the new data. How do we specify the new data? So here you need to say the maximum height to be equals to 50. And that's how we define the data set in R. So you can see that here I'm using data.frame. So in R, there are different types of data. We have vectors, we have matrices, we have lists, we have data frames. So these are all different types of data. I'm not going to get into a lot of details regarding the different types of data, but I want you to know that the most common type of data that you're going to encounter, let's say in a project, or let's say for this class, is basically a data frame. So that's why here you want to predict what will be the top speed for a roller coaster, that the maximum height of that roller coaster is basically 50. That's the way to do it. And then if you run this command, and then you can see what is the predicted value. Let's say for a roller coaster with the maximum height to be 50, then the top speed will be 42.1. That's basically how we do predictions. Now, similarly, we can expand this linear model to have a multiple linear model, or let's say you may want to have, let's say, polynomial model. Now, what you do is, I'm not going to get into the details, but I want you to observe that here, what I'm doing is I have the top speed, but I want to see what's the relationship between the maximum height and the maximum drop compared to the speed. So here I want to apply a multiple regression. Then what I'm going to do is the response should be before the tilde, and then after the tilde, you just specify all the explanatory variables. So have the first explanatory variable plus the second explanatory variable, and then you can run this command. Now you can also apply, let's say, a polynomial, or you can even apply a linear regression when you have a categorical explanatory variable. And if you remember in Excel, when you talk about the scenario about the neighborhoods in Seattle, and you have those 3 different neighborhoods, and in Excel, we have to manually create the columns for Bellevue and all these different neighborhoods. Now, the good news is that in Excel, in R, we don't have to do this manually. So let's say if I want to use a categorical variable, so let's say here I want to apply a multiple regression, and one of the variable is a categorical for the explanatory variable, then you can use the factor function. So the factor function is going to make that, is going to create those dummies variables for you. So you don't have to manually create those dummies variables as we did in Excel. And of course, you can also apply a polynomial regression. So let's say here, I want to apply a polynomial regression for the maximum drop as the response, and then I want the length, and let's say the square of the length. So what I'm going to do is I need to define the square of the length, and then I'm going to feed the linear regression. Here you can do a lot of different things regarding this ln function. Okay, any questions before we go and see the logistic regression? So the whole discussion here is when the response is a numeric variable, when I have quantitative variable as the response. And then I have one or more explanatory variables. Some may be numeric, some may be categoricals, some may be, let's say, squares, cubes, but the response is basically a numeric variable. Now, moving forward, and actually that's the thing that we want to explore in today's lecture, is what happens if my response now is a categorical variable. I have categories, I don't have numeric values. And let's assume that I want to see what's the relationship between the type of the coaster and the maximum height of the coaster. And let's plot this one to see what is the thing that I want to explore. Now, what I have in this specific scenario, my explanatory variable is the maximum height. We know that that's a numeric variable, it's taking different values. but now my response is a binary. And I have actually two types of clusters here. And I want to remind myself what are the different types. Basically either from steel or basically wood. So you have steel clusters or wooden clusters. So now you can see that my response is a categorical variable. Of course, you can fit a linear regression in this data set, but we're going to have the problem that you're going to make predictions that are outside of the range of the data. So we better apply the logistic regression. Now let's see how do we apply the logistic regression. Now let's see here. So I'm not going to create dummies variable, and let's see if it works in this specific scenario. Let's see how actually the data look like here. So let's say clusters, $sign, and then let's say type. Now, if you run these commands, then you're going to see that I have two groups, steel and wooden clusters. And then I want to apply logistic regression. Now, to apply logistic regression, we're going to use not the LM, not the linear model, but we're going to use what we call the generalized linear model, GLM. So the function that we're going to use will be GLM. We can use it exactly the same way as we have before. Let's say I'm going to have my response and also the explanatory variable. Actually, here it seems that we need to create a dummies variable for the response. So our response is basically steel and wooden, but I want to have it as 1 and 0. 1 will be the success, 0 will be the failure. And how can I do this one? So first of all, let's see the data. So the data look like this: steel, wooden, steel, wooden. I want to transform them into 1 and 0. So what I'm going to do is I'm going to go in the data, and if the type of the data is a steel, I'm going to assign it the value 1. If it's not steel, which is basically wooden, I'm going to assign it as 0. And then what I'm going to do is I'm going to rewrite this command. And let me run this command in the console. Now, if you run this command in the console, now let's see the data. Now, the data, okay, they're still basically, oh, I created a new variable here. Actually, here you can see the difference. So here before had time. Now I'm creating a new variable called cluster underscore type. So now let's go and run this command, clusters $sign cluster type. Now, if you run this command, now you can see that I translate the different categories into those 0 and 1. So 0 is when we're talking about the steel, and 1 if it's a steel, 0 if it's 1. And then you can actually create another plot here. If you run this plot, again, it's exactly the same plot, but now have 0 and 1 as the response. Now, once you create basically the dummy variable here, 0 and 1, now we should be able to go and apply the logistic regression. The function that we're going to use is the GLM. Before the tilde, you need to specify your response. The response is the one that you just created with the dummy variables. It's a dummy variable. After the tilde is the maximum height. The data will be the clusters, and then the family will be binomial. The GLM has a lot of different kind of regressions, but if you want to use the logistic regression, then the family here needs to be the binomial. Now, if you run this command, then we fit the logistic regression. If you click a summary, now here we can get all the different things that we want. So we want basically the beta 0 hat, the beta 1 hat, that's the intercept. This is the slope. So we get all the necessary information. So here I also show you another way to do that. And then the most important thing is, how do we make predictions? Let's say for a specific cluster with a specific maximum height, how can I see if it will be made of steel or wooden? And to do that, what I'm going to do is I'm going to use the predict function again, the same as what I had before. And then here, let's see how to do predictions. The function is the predict. I have the model LR, logistic regression model. And again, you need to specify the data. Now, if you run this command, then we're going to be able to get the prediction. But be careful. Now here, this one, this value is not the probability. This is the value of the logit. So let me show you the slides. So let me remind you. So, okay, that's not what I want. So on the slides, if you remember, that's the logit. The value that you get is basically the logit. If you want to get the probability, what you need to do is basically you need to transform and go back and find the probability. And here I'm showing you the function that you need to run. And then you can run this command. And now this is going to give you the probability. So let's say for a roller coaster with a maximum speed of 30, then the probability that is going to be made of steel is 0.27. Now, how can you make a decision? If this probability is less than 50%, then you're going to assign it to 0. If it's greater than 50%, you're going to assign it to 1. Now, this probability is very small, so then you need to say that for a roller coaster with a maximum height of 30, then most likely this will be made of wood. It will be a wooden roller coaster. Does it make sense? So here, it's exactly the same steps as we were talking about the linear model, but now it's a different function that you can apply, the GLM. And then again, when you make predictions, so you get the value, but this value is this one. But in the logistic regression, I want the probability. So then you just apply this transformation, and this is going to give you the probability. Okay, any questions, any comments, any clarifications? Now, what I want to do next is let's see some more techniques, some more machine learning techniques. And then after you're done with these techniques, I'm going to show you how you do them in R, and then you can work on the today's handout. Okay, the next method is what we call decision tree. This is a supervised machine learning method, often used for classification. We can use decision trees for both classification and a regression, but in most of the scenarios, we use the decision tree for classification. Now, what is the idea here? The idea is that I have some variables and I have some categories as my response. Let's say you have two categories. Now, the idea is first, you're going to choose the variable that is more significant. Actually, I don't like the word significant here. Let's say I want to use the variable that can give us a better idea of whether it's group 1 or group 2. So in other words, what I'm going to do is I have different variables, different explanatory variables. And then the first one is I'm going to select an explanatory variable that split the response the most accurate way. And then you keep doing that until you get what we call pure decisions. All these will make sense once we go to the example. Let's go in the scenario. We're talking about the Biden and the Trump election, 2020. I would have a model that for a single individual, it can tell me, okay, based on some information, what that individual could have voted, let's say Biden or Trump. Now, in our data set, the first variable that can really make a very nice distinction between those two categories is basically what political party are they registered under. So in other words, if they're Democrat, then it's most likely that they're going to vote for Biden. If they're Republican, they're most likely that they vote for Trump. So that's a variable that is the most important one to differentiate between the two categories. Now, once you differentiate, once you use, let's say, these variable, then we keep going and adding more variables. Let's say for Democrats, here, the next question that you need to ask, the next variable that can further categorize my observations into those categories is basically where do they live? So for example, if they live in suburban or in the urban compared to the rural. So for example, if they live in suburban and urban, 50, they vote for Biden, 4 for Trump. If they live in rural, 23 for Biden, 20 for Trump. Now, for the Republicans, on the other hand, there may be another variable that really help us distinguish between those two categories. And maybe in this specific scenario is whether or not they have a college degree. So for example, if they had a college degree, then 40, they vote for Biden, 48, they vote for Trump. If they didn't have, 1 vote for Biden and 34 voted for Trump. And you keep doing that until you get some pure, let's say, results. So you keep using variables, and then at the end, you're going to have a group that is only Biden, only Trump, only Biden, and only Trump. And what is the logic here? The logic is here is I get information for an individual, I get all these different information, and then I'm just following the tree to make a prediction. Let's say for one individual, I'm going to ask you, okay, what political party are you registered under? So maybe they're going to say Republican. So then I'm going to follow this graph. The next question that I need to ask is, do you have a college degree? If they said yes, so I'm going this direction, and I'll keep going. And then at the end, there will be a decision whether, let's say, these individuals, they vote for Biden and they vote for Trump. Can you see of any benefit or any advantage of those specific techniques? Let's say the decision trees. What is a good thing about this technique? Yes.
You can split the data into more categories.
Which means, yes, I agree.
It's a little more accurate.
It's more, I will not say more accurate, but it's more interpretable. So let's say when you talk to high school students, if they do classification and they create a decision tree, it's very easy to explain this tree to the student. Let's say, how do you make predictions? You just follow the tree, and then at the end, you're going to have a decision at the end of the tree. So the advantage actually of the decision tree is that it's very easy to explain, okay? And it's more like asking questions. It's important to follow the correct order. So that's what the statistical method is doing, the machine learning method is doing, is using the data, checking the variability, using entropy, a lot of different things. I'm not going to get into the details, but the idea is that the machine there is choosing the variable that can really affect the results and then create that state. And they keep doing for the next one, the next split, keep doing until we get at the end results that are only Biden or only Trump. And then you just follow the diagram to make a prediction. Now let's see how to do that in R. So again, I have the command here to run a decision tree. Now the bad news is that there is no built-in function in R to run, let's say, the decision trees. We need to install some packages. And how do you install some packages? So here I have 2 packages that you need to install. One is the R part, the other one is the rpart.plot. What you need to do is you need to run these 2 commands. I'm not going to run them on my computer because I have already installed the packages. So you need to install those packages once. Be careful. Be patient. It may take a while to install these packages. This includes a lot of functions, a lot of different things. So basically what you need to do is copy and paste these commands in the console, the R part and also the rpart.plot. Run this command in the console. You may need to actually restart the RStudio after you install. And then once you install these packages, then what we need to do is we need to load the packages in RStudio. And how do we load these packages? You need to use the library command. So here, because I have already installed the packages, then what I'm going to do is I'm going to just run the library. And then I'm also going to run the library for the rpart.plot. If you have successfully installed the packages, then when you run the library, you shouldn't really get any error or any, let's say, mistake there. It should be run smooth. Warning signs is okay, no problem. but you need to be able to load the packages. Okay, now once we install the packages and we load the packages in R, now how do we run the decision tree? Again, it's very simple. So in R part, this is a function that we're going to use. Again, we're going to use the tilde sign. And then let's say here, what I want to do is I want to predict the type of the roller coaster, either steel or let's say wooden, based on the different features. The top speed, the maximum height, the maximum drop, the length, the age, and the design. And then I'm going to use the data that I defined before, which is the coasters data. Now, if you run this command, so basically you create the decision tree, and the way to visualize the decision tree is by using this rpart.plot function. So if you run this command, now you can see that now we have the decision tree for this specific scenario. So basically, let's read behind this decision tree. So the first variable that can affect, let's say, the type of the roller coaster is basically the maximum height. If the maximum height is greater than 128, then it will be a steel. So the decision that you're going to make is basically steel. Now, if the maximum height is less than 128, then the next question that you need to ask is, okay, what about the length of the roller coaster? If the length of the roller coaster is less than 2621, then there's another question here. It says, okay, what is the age of the roller coaster? If it's less than 49, then basically you classify it as a steel. If it's greater than 49, you grade it as a wooden. And then similarly for the other direction. If the length is greater, then you go in this direction. Then what is the design? If the design is inverted, go in this one. If it's other, go the other one. So here you have a nice visualization how to make decisions for this specific scenario. And this is what we call a classification problem. The response has different categories, and then you try to assign these, you want actually try to predict those categories based on different values of the explanatory variable. Any questions, any comments, any clarifications? And then the last technique that we're going to cover, and then go to go in the handout, is basically what we call the k-means cluster. This is an unsupervised learning. And why it's an unsupervised learning? Because now we will not have a response variable. I don't have any variable that I want to predict, but now it's more kind of an exploratory data analysis. I have some variables, and I want to see if there is any kind of grouping between the categories. And here I'm going to use what we call the k-means clustering. So it's a method of partitioning n observations into k clusters, where each observation is assigned to the cluster with the nearest. Now, what is the logic here? Let's say you have two variables, x and x1 and x2. You don't have a response, but now more or less, you can even see from the graph that there may be some kind of grouping here, or let's say if you want to use them, you may see them all together. But the goal of the cluster is basically try to see if there are any common things across those two different variables. And then what we're going to do is first, basically what these methods does is basically first is randomly choosing two centers for, let's say, the clusters. Let's say first you need to define how many clusters you want, how many groups you want to do. So then the machine here is choosing two centers for these clusters, and then it's calculating the average distance of basically the points to that center. Calculate not the average. It's calculating the distance of the point to the center. To the point to the center, you just get all these different distances, and then at the end you find the average distance of all the data points to the points. And in this way, you can recalibrate the model and then choose a more suitable center for the clusters. And then you keep doing it until you get some nice clusters. And here, let's say, if you specify the cluster to be true and you apply the k-means clustering, you're going to see that these methods, these data points are clustered together. These data points are clustered together. And what can we gain in this scenario? Maybe the observations in the first group has some specific characteristics. The observations in the second group, they may have different characteristics. And then you can do similar thing. Maybe you apply, let's say, 3 clusters. You can apply the k-means clustering, and this is going to create the 3 groups. These clustering techniques are actually very challenging because I'm not sure if these groups are correct or not, or if these groups make sense or not. I don't really have a response variable. It's just one way to perform some kind of exploratory data analysis. And let's see how we do that in R. So again, we need some more packages, ggplot2, and then factor extra. So please run these commands first, install them. Once you install them, then we need to load these packages in R. So for me, I'm gonna just run the library commands because I've already installed this one. And now let's see how we apply the cluster. First of all, let's see what's the relationship between the top speed of a cluster and the age of the cluster. So here we can see what's the relationship between these two. Now, what I'm interested to see, I want to see if there's any kind of grouping between those different observations. Then I'm going to run the k-means function. I'm going to specify the data. Basically, the top speed is in the 4th column. The age is in the 8th column. So that's why I'm defining the data like this here. And then I'm saying I want 4 centers, 4 clusters here. And if you run this command, then I'm going to save in the data the different clusters. And then I'm going to use this command fviz_cluster to basically create the clusters. Now, if you run this command, okay, now basically we get the data set, and now we can see the different clusters. So I have the top speed, and then I have the age. Now we can see that there are different groups here. For example, this group consists of quite old, let's say, roller coasters. So you see the age is quite large for these roller coasters. And then you have roller coasters that they're not so old, but then within these ones, I have again different groups. And maybe there's some characteristics. If you go and check all these, let's say, data points, maybe these ones, they have a specific characteristic, or this one, they may have different characteristics. So it's more about exploring the data, playing with the data, and see if there are any interesting pattern or relationships between the data. Okay, that's what we call clustering. Any questions, any comments, or any clarifications? Now, what I want you to do for the next, let's say 40 minutes is go in the lecture 4 handout. So I assume that you're done with the first exercise. Now I'm asking you to go and do the second exercise. The second exercise is basically telling you to become the judge of a DataJam competition. So you go on the website, you choose a project, and then I'm asking you to get some more information regarding the specific poster. I want you to tell me what techniques they have used, what results they get. And also at the end, I really want you to evaluate the poster. And here I gave you basically the rubric that the judges are using at the DataJam competition. So I really want you to follow this rubric and then evaluate the poster that you choose in this specific scenario. And then I have one question about the paper that I asked you to read for this week. Okay, so I think I'm going to stop here for today. Do you have any comments? Yes.
I do. I'm very, very excited about you using the judging rubric. We want to see your results. So definitely do this, definitely turn it in. We are revising the DataJam judging rubric, and we have several members of the board of directors of the DataJam working on this. These are professional data scientists, and later this semester, we will have you use the new rubric also, but we would like to compare how you use the old rubric and how you use the new rubric. So this is a very exciting thing for us to see you do this. I also want to make a couple of announcements. All of you now should, both at Caldwell and at Pitt, should have received an invitation to the fall 2025 DataJam Slack workspace. Please accept that invitation. I'm only allowed to invite so many people, and it is blocking me from inviting everyone on the teams because the mentors, most of you have not accepted. Some of you have accepted. But please just go into your email, accept it, and get on the Slack workspace so that I can invite rest of the people. I have received emails back from my inquiries earlier in the day from some of you that I emailed asking if you were available at the time you said you were going to be available to be a mentor. If you've not emailed me back, please email me back because I would like to assign mentors, but I don't want to assign mentors unless I'm quite certain you can meet with the teams at this time you did. Because the next thing I'm going to do is connect you to the team. But I don't want you to say, oh, I'm sorry, I can't meet them, because the teams also gave me times they could meet. And the reason I emailed you is because your available time matched with the team's available time. So please confirm with me if I emailed you, and then I'll connect you to a team to mentor. And then lastly, I sent you the code of conduct form that you need to sign to be a DataJam mentor. Please sign that and send it right back to me. Okay, thank you.
Sounds good. So please start working on the handout. If you have any questions, feel free to let me know.
I'm delighted to see that as I was talking, 9 people accepted the Slack invitation. Thank you, thank you.